An overview of high impedance differential. Scheme, design, protection, and simulation for a 132 kV double busbar single breaker system. Abstract. This paper illustrates the common practical schematics used for high voltage busbar protection. The schematic includes the detailed high impedance AC circuit including shunt and series resistors, nonlinear resistors, Metrosils, current transformers, supervision relay circuit and overcurrent relay. The design criteria for each component that ensuring correct selectivity. The DC schematic includes the discriminative and check zones which determine the tripping criteria in which the protection will operate to protect the busbar and how it is achieving optimal reliability. This paper demonstrates both primary and secondary circuit simulation during internal fault condition by OMICRON RelaySim test and PSIM softwares with and without Metrosils approaches. Keywords: high impedance differential, busbar protection, RelaySim test, PSIM. Introduction. Busbars have the highest rating among all the connected electrical equipment in any electrical substation. That's why they are the most vital part, and if its protection fails for any reason, all the substation might be out of service or blackout. Hence protection engineers had to find a method to protect it in proper and selective way. High impedance differential is one of the most economical, practical, and easy to troubleshoot method for protecting EHV, HV and MV busbars compared to other protection methods, as it uses a simple circuit and one simple overcurrent protection relay for each busbar under protection, unlike low impedance differential that uses number of slave protection relays equal to the number of feeders connected to the busbar under protection, in addition to a master relay having physical communication with the slave relays. In this paper we will go through the high impedance differential protection for a double busbar and single breaker in 132 kV high voltage substation. 2. Double busbar single breaker system. Double busbar and single breaker system is commonly used in high voltage substations, either air insulated switchyard, ACE, or gas insulated switchyard, GIS, as shown in figure 1. The used busbar is divided into 4 segments, 1A, 1B, 2A and 2B, connected by means of bus couplers and bus sections to provide a wide range of reliability in feeding and switching. Fig 1. Double bus single breaker system. 3. High impedance differential AC. Schematic. The primary AC circuit is simply a 4 segments double busbar and some connected electrical bays through a circuit breaker and some isolators such as overhead transmission lines, underground cables, grid transformers, shunt reactors or static VAR compensators, SVC. As shown in figure 2, each bay has 2 CT cores assigned for busbar protection. These CTs should have same ratio, same polarity with respect to the busbar direction, same magnetization current IM and knee point voltage V, K, and same class. The recommended classes for high impedance relays as per IEC standard IEC 60044-6 Annex D, are Class TPS and Class TPX as it has low leakage flux properties. The secondary circuit of one CT core in a bay will be connected directly in parallel with the corresponding bay's CT cores in same direction and polarity to result in one loop with 2 ends to be connected together as a ring to ensure reliability if any cut occurred in between, and to be interfaced to what's called busbar check zone protection panel so that any current difference between busbar as a single piece inputs and outputs will flow through the loop to the check zone protection relay. As per Fig. 3. Fig 2. CT cores primary circuit connection diagram. The secondary circuit of the other CT cores will be connected in similar way of the first core, but through the isolator status to discriminate the related bay is connected to which busbar segment 1A, 1B, 2A or 2B, and result in 4 ring loops to be interfaced and terminated to what's called busbar discriminative zones protection panels. So that any current difference between inputs and outputs in one busbar segment will flow through the corresponding loop to the related discriminative zone protection relay as per figure 3. Or Metrosils R, NLR, CT supervision relay, 95B, and high impedance differential protection relay, 87B, that will be described in details. 4. High impedance differential circuit. Design. The secondary equivalent circuit per phase is as per figure 4. Fig 4. High impedance secondary equivalent circuit where R, LCT lead resistance between healthy CTS and a saturated CTR, L lead resistance between all CTS and the high impedance circuit. CTS PVN, CT supervision relay. R, NLR nonlinear resistor. R, SH shunt resistor. R, S series resistor. R, R protection relay equivalent resistor. I, FS secondary fault current. I, NLR Metrosil leakage current. I, S relay set current. I, SH current flowing in shunt resistor. V, S relay set voltage. We will design all high impedance circuit components according to data extracted from a practical case field project as per Table I. Table I practical field data. Parameter value. R, LCT, 0.50 R, R, 0.050. R, CT, 50 Noah Bayes, N, 10. R, L, 50 km 600/1. ISK 40 kb 2000/1. V, K, 500 V I'm 25 mA. A design of relay set voltage V, S. It is the voltage across the shunt resistor R, SH, at which the protective relay should operate. To design this value, we should take into our consideration that this voltage is also applied to all CT secondary circuits in parallel, so V, S, should not reach half of the knee point voltage of the current transformers V, K, to avoid CT saturation. V, S. 1. V, S. Then V, S. In case of external faults, heavy currents will flow through the system bays resulting in zero current difference in CTS theoretically, but in practical case there is a possibility for at least one CT to be saturated. In this case all CTS summation current will flow through the saturated CT, which is specified by its secondary resistance R, CT, as it is the smallest resistance. Path. Taking into consideration the lead resistance between the healthy CTS and the saturated CT, which is R, LCT, noting that the parallel resistors have a big value compared to R, CT, so it will be neglected. Since the protective relay should not respond to external faults, so V, S, should be greater than the resulting voltage as per equation 2. V, S. Dot, 2. V, S. Then V, S. Where, ISK is primary maximum fault current and KB is bus bar. CT ratio. From equations 1 and 2, we can select V, S, equals 150 V. B design of relay set current I, S. It is the protective relay pickup current value and can be selected so that it should be higher than the relay function minimum current setting and should not be very high in order to minimize the circuit burden and hence the resistors ratings. We can use Siemens 7SJ64 relay for example, which having minimum current setting equals 0.05 A, so we can select I, S, equals 0.1 A. C design of series resistors R, S. In case of external faults and one of the CTS is saturated, an amount of voltage will be applied to the protective relay and can easily make it operate unless a series resistors, sometimes named as stabilizing resistors, are connected so that the protective relay shall operate only if the applied voltage is greater than V, S. D design of shunt resistors R, SH. Many busbar high impedance differential protection schemes were designed without shunt resistors, but it has been recorded some protective relays maloperations due to differential current produced by the following cases. 1. In case of heavy current external faults and there is no any CT saturation but due to CT error that is not equal for all the used CTS, a differential current might be produced. 2. In case of switching or sudden tripping of any heavy current bay connected to the bus bar, that leads protection engineers to set a minimum sensitivity current limit that can operate the protective relay. The following practical equations are commonly used. I, K, 4, I, K, 5, where imp is the minimum sensitivity primary current, Km is the CT ratio of the lowest load current Bay. We can use equations 4 and 5 to select the value whichever greater for imp, and if it is referred to the secondary circuit will be I, SH, I, S, I, NLR, I, SH, I, S, I, NLR, 6, where IMS is the secondary current of imp, IMS is the busbar CT magnetization current at relay set voltage V, S. Noting that equation, 6, should be in vectors but we used it as a magnitude. Design of nonlinear resistors, Metrosils, R, NLR. During internal faults, heavy current will flow in the high impedance circuit which will make it subjected to a transient high voltage until the fault clearance. This high voltage can damage the whole circuit insulation. That's why we need a voltage function resistors called Metrosils to suppress the high voltage by providing a low resistance path. First we need to check if the maximum RMS voltage during maximum fault current more than the maximum permissible voltage of the relay system, then if yes we will need Metrosils. We shall select the maximum protection voltage from data sheet so that the relay system insulation can withstand as per table 2, for example most LV equipment can withstand up to 1 kV. The Metrosils can be specified by the maximum continuous voltage rating, VR, and leakage current at relay setting voltage. The maximum continuous voltage rating, VR, should be selected more than the relay set voltage V, S. V. Dot. V. S. 10, we can calculate the leakage current at relay setting voltage, from the following equation. Dot. 11. Where C equals 450 for V, S, equals 185 V and SS equals 0.25. So in our case V max equals 4.7 kV, VRMS equals 3.3 kV. Equals 12 mA. Then from the Metrosil manufacturer data sheet we can select the suitable model as per table 2. Table 2. Metrosils model selection. F. Design of CT supervision relay. In case of minor disturbances for high impedance secondary circuits such as wiring, loose connection can introduce amount of voltage across the protective relay but still will be less than the minimum operating value V, S. A CT supervision relay is required to protect the circuit by shorting the CTS as well as giving alarm to the operators to investigate the problem reasons. We can consider that there are disturbances if the primary differential current more than or equal 125 A or a 10% of the CT ratio of the lowest load current Bay, whichever is the greater. For simplicity, I, FP, K, 12, where, I, FP, is the primary differential current due to disturbances and its minimum value is 125 A. Then we calculate the voltage across the CT supervision relay as following. Dot. Dot. V, CT SPVN. I, FS. R, SH, 13. Dot. Dot. So in our case V, CT SPVN. V. V high impedance differential DC schematic. Typically there are 5 protective relays, 4 relays for the discriminative zones to protect the busbar segments, 1A, 1B, 2A and 2B, and is acting as a main protection. 1 relay for the check zone to protect the busbar as a single piece and is acting as a backup protection. Each protection has an in/out facility to put the relay in service or out of service, a CT supervision relay that could be healthy or unhealthy, operated, and a protective relay that could be in operated or not operated state. As per figure 5, the tripping criteria are contribution from both discriminative and check zones, where the discriminative zone supplies the positive terminal of the busbar trip relay 86 BB and the check zone supplies the negative terminal. As per figure 6, there are 5 tripping cases out of total 9 cases. A correct tripping case should include at least a confirmed operation from one protection, either check or discriminative relays, and the other protection has either a confirmed operation, out of service, or CT supervision unhealthy. Bus bar should not trip for other 4 cases since there is no a confirmed operation. 6. High impedance differential. Simulation. Considering a 10 base GIS double bus bar and single breaker 132/13.8 kV substation includes 4 overhead transmission lines, 3 grid transformers, 2 bus couplers and 1 bus section as per figure 7. Fig.7. System under fault simulation. As per table I, the maximum short circuit current is 40 ca. We will simulate a 3-line to ground fault in bus bar 1B using RelaySim test and PSIM softwares. Fig.8 shows the system voltage and differential current at normal condition. Fig.9 shows the system voltage and primary and secondary differential current at time of LLL to ground fault condition. Fig.9. Bus bar 1B differential current during fault. Fig.10 shows the simulated secondary high impedance circuit updated with the data calculated from the design section. Fig.11. Secondary circuit without Metrosils analysis. Considering the complete circuit with Metrosils of type 802/600AS3/I, that have a maximum protection voltage Vmax equals 1435 at maximum RMS fault current I, Fs, equals 50A. It is noticed that the RMS voltage across the relay as per figure 11 is limited to around 405 V so that the relay system insulation can withstand. 7. Conclusion. It has been discussed high impedance bus bar differential protection, which is one of the most common, practical, and economic schematics used for bus bar protection. We went through its AC and DC circuits illustration, design for each component. We compared the old circuit design without shunt resistors with the new common design with shunt resistors and how much it is important to get rid of protection malapplication. We demonstrated a 10 base system bus bar high impedance circuit simulation with and without Metrosils to prove its merit. 8. Acknowledgement. I would like to pay my special regards to my family, especially my parents, my wife, and my son who encouraged me. I wish to express my deepest gratitude to all people whose assistance was a milestone in the completion of this work.